In this lecture, we will be studying the concept of asset returns. So first, let's start out with the basic model for an asset price. So we'll have an asset, it will have price P sub t at time t. And it could be any asset. So it could be a stock, it could be a bond, an option, a futures contract, a forward contract, the value of a house, the value of a car, the value of a horse. It could be any asset at all. And we are going to think of it as the price of an asset at the end of day t. So we're going to be thinking in terms of holding an asset from time t minus 1 to time t. And it will be natural for us to think of this as the tth day. So think of it like you start the ownership of your asset at the very end of the previous day. So think of it as like right after midnight up until midnight on day t. This works with any time scale, but it's going to be most intuitive to think of it daily. So we want to think of it like stock price. So this period of time is like holding the stock on that tth day, and P sub t is the price of the stock when the market closes at the end of that tth day. Now the first type of return we look at is the net return. So again, we have PT, this is our asset price at time t. The net return, which we use capital R sub t, over the holding period from time t minus 1 to time t, is defined as this expression here. So thinking about our asset, let's choose the example of the stock. This would be, again, when we're holding that stock over our time period t minus 1 to t. And so think of it as we're holding it over the period of that tth day, from the beginning of the day till the end of the day. Well, how do we get the net return from that? We take the price at the end of the day minus the price at the beginning of the day. So the numerator here is the change in the price, and then we divide it by the price at the beginning of the day. You notice this simplifies to this expression here. If we break up this fraction, you have pt over pt minus 1, and then minus pt at minus 1 over pt minus 1, which is minus 1. So this is a percentage gain. So again, the percentage gain we earn by owning a stock over that period, that tth day. And note that it doesn't depend on currency. If you look at this in terms of units, you have, if you were using American dollars, you would have dollars in the numerator and dollars in the denominator, which cancel. And so you get something that is a percentage. And so, for example, if you have a stock that was, say, worth $100 at the end of yesterday's trading day, and so you buy it you come into the market this morning, you buy it at $100, and at the end of today it's worth $110, then we know just intuitively that the percentage return you made on that was 10%. But we can see that reflected here. So we would have 110 minus 100 in the numerator divided by 100, or 10 over 100, or 0.1, which is our 10% return on a percentage basis. We now move from the net return to the gross return. And the gross return is defined in the following way. So we have our same asset price, the simple gross return. We write it as 1 plus RT, where RT is the net return. So the simple gross return over the same holding period is 1 plus RT, or the ratio of the price at time t to the price at time t minus 1. So the gross return, the simple gross return, or what we mean by that is single period gross return, is nothing more than 1 plus the net return. And so you can think of this in that previous example where we had PT was 110 and pt minus 1 was 100, then in that case, we just take the ratio of the two, and we see 1 plus RT is 110 over 100, or 1.1. And so you could think of that as 110%. So the gross return, intuitively, you can think of it as it gives you that net return, that 10%, plus the 100% that you have from retaining your ownership of the investment. So that's how you can think of the gross return. But again, it's just a matter of adding 1 to both sides of the net return equation. So recall that our net return equation on the previous slide was R sub t is pt over pt minus 1 minus 1. And so if we add 1 to both sides, we recover this equation 2 here. So that gives us our net return and our gross return. But the key thing to recognize is that this is for a single period. In the context we're thinking of, for a single day. Well, what if you wanted to look over k periods or k days? We then define the gross return over the most recent k periods, and we define it in this way. And so the way to imagine this now is you're here on day t minus k, and you hold it up to time t. So your holding period is now this multiple period interval. And we can see how we get the formula, because the gross return over our most recent k periods, intuitively, think of it in the same way. We take the value of the asset at the end. So here, right, that's our PT is here. And we divide it by the value at the beginning. If you subtract 1, that gives you the net return over that period. If you don't subtract 1, that gives you the gross return over that period. So this is the intuitive way to define that gross return. And here would be your net return over k periods. But we then can do a little bit of algebra to note that we can rewrite it in this way. And notice what we're doing here. Here, we are just pairing. So we add in this pt minus 1, but notice we do it top and bottom, and those cancel. Pt minus 2 will have a partner in the next term. This happens up until you have a partner here for that pt minus k plus 1. The way to not be confused by this subscript here is just to note that t minus k plus 1 is just one time step after time t minus k. But the key thing to recognize here is that each one of these is nothing more than a single period gross return. This is the gross return for day t. Here. This second fraction is the gross return for day t minus 1. Here. Up until the end, the last fraction is the gross return for day t minus k plus 1. And so we see that the k period gross return is the product of the single period gross returns. And so this is an important insight. We'll see why it's so important in just a moment. The next type of return that we will look at is the log return. And so our definition of the log return is, again, given capital PT as the asset price at time t, and little pt, which is the natural log of capital PT, as the log price. The log return, and we use small r sub t, over the same holding period, time t minus 1 to time t, is defined in the following way. And you take the natural log of the gross return. And we see another way to write it here, natural log of the gross return from the definition of gross return. And we do this because we can then use the property of natural log that it turns the natural log of a quotient into the difference of two natural logs. And so the property of natural log gives us that this is natural log of capital PT minus natural log of capital PT minus 1, which are the log prices, little p t and little pt minus 1. So this is a very handy relationship that the log return has with the log price. The log return is the difference of the log prices. This comes up a lot in continuous time finance. So when we have continuously compounded returns, this becomes very handy, and it comes up a lot in all kinds of financial modeling, and we are going to see explicitly why. The first reason we're going to see why is you can use this, you can use the log return as an approximation to the net return. So this equation here, little rt is natural log 1 plus big RT. Let's think about that. Let's recall from calculus our Maclaurin series for the natural log of 1 plus x. So we have the result from calculus that for absolute value of x less than 1, natural log of x is equal to its Maclaurin series, which is this alternating series here. So negative 1 to the n plus 1 times x to the n over n. So if we plug in n equals 1, we see we get minus 1 squared times x to the 1 over 1, which is x. If we plug n equals 2 in, we get minus 1 cubed, so a negative sign, x squared over 2, and so on and so forth. And you can see the reason why we have a finite radius of convergence for this series is these are not factorials in the denominator. So the problem is the denominator is just not growing fast enough as you move down the list for this series to converge everywhere. But the key thing to recognize is absolute value of x less than 1, thinking about that as an interval, that means we're working on the interval minus 1, 1, 0 is the midpoint. Well, let's think about taking a first order approximation to the function natural log of 1 plus x using this Maclaurin series. If we do that, that means we're just pulling off that first term, which is x. So that gives us our first order or linear approximation to the function natural log 1 plus x from this Maclaurin series. Well, now let's think about letting x be replaced with the net return, RT. Now, it's typically true that your net return in size is less than 1 for a small time scale. Think about what it means. If your net return is 1, that's a 100% return or a doubling. On smaller time scales, that tends to not be standard behavior for assets. If we go the other way, if r sub t is equal to minus 1, that's a 100% loss. So in a stock, for instance, you're wiped out. Not necessarily true in some other positions where you're shorting things, but if you have a long position in a stock, a negative 100% loss wipes you out, and nothing down here to the left of minus 1 makes any sense. But most of the time, your net returns in most applications are clustered near 0 inside the interval minus 1, 1. Point being, this is usually a valid move. It's usually valid to use this natural log 1 plus x as approximated by x. So let's just go ahead and replace x with RT. If we do that, we see here we have this approximation. We plug x in. We plug RT in for x. This is what results, and we notice that on the left we have nothing more than the definition of the log return. So we see that the log return is an approximation to the net return. Thus, in financial modeling, we often work with which is more convenient. Now, the log return may seem strange because the net return seems like the natural thing to use. That's kind of pure in the sense that it just gives you your percentage return on an asset over a holding period. Why approximate that? Well, we do that because of the following property for log returns. So the K-period log return is defined in the following way. We write it as little r sub t of K to show that it's the log return over the most recent K periods. And to do that, we take the log of the K-period gross return. So in here, it's important to note this. That's what this is here. That's the K-period gross return. So we take the log of that, but recall that the K-period gross return was the product of the single period gross returns. And so we make that substitution here. We then note that log turns products into sums of logs. So this expression can be rewritten as the sum of the logs. So we have natural log of 1 plus RT, and then plus natural log of 1 plus R t minus 1, all the way down to the last term, natural log of 1 plus R sub t minus k plus 1. And then we note that these are nothing more than the single period log returns. And this is important because this is a fundamental difference between K-period log returns and K-period gross returns. We see here the K-period log return is the sum of the single period log returns. Again, recall, the K-period gross return is the product of the single period gross returns. This is a very substantial difference between the two, and we will follow up on this and see how this becomes really important in financial modeling. But we really have covered the key different returns here: the net return, the gross return, and the log return. So it's very important to understand these three and how they relate to each other, because they really are fundamental in finance.